Hello, welcome to the course on modeling transport phenomena of microparticles. So, this is done by two professors S. Bhattacharya and G. P. Rajshekhar, both Department of Mathematics, IIT Kharagpur. Okay. So, as the title suggests, modeling transport phenomena of microparticles. So, what we would like to do in this course is we would like to run through basic tools to understand the transport of microparticles. So, when we say microparticles, typically these are like viscous drops, soft colloids, microorganisms or rigid colloids, etc. Most of these you can see in various applications in viscous environment, and sometimes in addition to viscous environment you will see some external gradients like temperature or concentration or sometimes electric field, etc. So, the basic aim of the course is to give you some analytical tools, and then once that is done, some computational tools. Okay. So, let us see the module 1. Module 1 is preliminary concepts, fluid kinematics, mass conservation and stress. So, these are the preliminary concepts. So, when we say fluid kinematics, so typically when we start with fluid kinematics, one would try to understand the basic continuum hypothesis. So, what is continuum hypothesis? Typically a textbook definition is one-to-one correspondence between the matter and the space occupied by the same. So, which means it is like this. So, you have an object. So, now I kept here. So, there is a one-to-one correspondence between the space occupied by the matter of this. Suppose if you move it, so then again there is a one-to-one correspondence. So, there is it is completely continuum. Okay. So, according to this, for example, any fluid property like density, velocity, pressure, temperature. So, they continuously depend on position and time. So, it's once we have the continuum hypothesis, typically fluid motion is described with the help of two approaches. One is Eulerian approach and other is Lagrangian approach. So, what is the big difference between these two? So, the Eulerian approach is like we are sitting on a particular position, and then let us say we are looking at it at that instant, whereas Lagrangian approach is like we are tracing the trajectory. Okay. So, let us see in detail Eulerian coordinates. So, typically we are using a small x bar x1, x2, x3 Cartesian frame. So, here it is nothing but labeling points, which means we are working in a fixed laboratory frame. That means a position is fixed. So, you are observing who is passing by this at a particular time, who is passing at different time. Okay. So, this is Eulerian approach. Okay. So, a position is fixed and all particles pass through this at different times, that is what we are observing. So, accordingly, for example, if you talk about velocity u bar x bar t, this is nothing but fluid velocity at this position at this time. Okay. So, now corresponding to this Eulerian coordinate frame, what is the time derivative? So, what we say is the position is fixed. Okay. So, therefore, the Eulerian time derivative is defined as the rate of change with respect to time while x bar is fixed. Okay. So, now what is Lagrangian coordinate? So, this we are denoting by capital X bar, again Cartesian frame, and as I already indicated, it is labeling fluid particles. Okay. So, that means you are labeling a particle and then you are observing. Okay. It is like we are at a far off and then we are trying to see how a particle is moving. Okay. Something like that. Okay. So, accordingly at t naught, so this is the reference position vector. At time t, the position vector is expressed, however, you see in terms of the reference. That means we are labeling the fluid particle with this reference position and then we are tracing. Okay. So, for example, if you take density, so this is explicitly in terms of the reference variable. Okay. So, now what these are corresponding derivative in the Lagrangian frame. So, this is called Lagrangian derivative or material derivative. So, this is given this notation. Okay. That means there is something more to be understood about this, which we will. So, you will see here it is a rate of change with respect to time with reference position fixed. So, for example, if you take the position vector expressed in terms of this reference variable, so the Lagrangian derivative is the velocity, but you can see the position vector is expressed in terms of the reference variable. Okay. So, what is the basic difference? So, in one approach we have fixed the frame, okay, and in Lagrangian we have taken a particle. So, at t naught, so it is at some other time, okay. So, at some t k. So, this is a trajectories, each particle. So, this is a particle 1, particle 2, particle 3. So, we are tracing the trajectories. This is the Lagrangian. So, this approach you are observing sitting on that, okay. Then at that instant t. So, this is nothing but. So, here we have a reference attached. So, for example, this is kind of, okay. So, this is the basic difference. So, once you have such a description, then definitely we would like to use back and forth depending on the convenience. So, the natural question to be asked is, once you are given one description, how do you get back? Okay. So, naturally this is nothing but a coordinate transformation. So, for any coordinate transformation, what you require is the corresponding Jacobian, right. So, that is what we are defining. So, as per the continuum hypothesis, there exists a one-to-one correspondence between Lagrangian description and then Eulerian description. So, we assume that this map is continuous, so that the Jacobian is positive and bounded, and this determinant is non-zero by virtue of this. So, that the mapping is invertible and one can play with various descriptions. Okay. So, correspondingly for any physical conditions, you take it and then model, and then let us say you try to play with the corresponding coordinate systems, then you need some volume element. Okay. So, you see the volume element in Eulerian description is Jacobian times the volume element in the Lagrangian, and you can see this Jacobian at time t equal to 0 must agree with 1, because the position is agreeing with the reference. Okay. So, that means there is no coordinate transformation, right. So, what is the use of this? Use is like one can change the coordinate systems, Lagrangian to Eulerian and Eulerian to Lagrangian using inverse transformation. Okay. So, we will see the use of this very soon. So, this can be expressed in this form, in a compact form. This is the summation notation. Maybe in some exercise I will include a few problems on summation notation, so that you can comfortably follow. Okay. So, this Jacobian can be expressed in this form, where epsilon I j k is a Levi-Civita symbol, and the definition is hinted here. So, this is 1 if I j k in cyclic order, minus 1 acyclic, 0 otherwise. So, what does it mean? It means, so you consider epsilon I j k. So, suppose you take epsilon 1 to 3, since these are in cyclic order, the value is 1. Similarly, suppose 2, 3, 1. So, they are in cyclic order. Okay. Suppose 1, 3, 2. So, the cyclic order is disturbed, they are in a cyclic order, so the value is minus 1. Similarly, suppose if you take 1, 3, 3. So, there is index repeated. So, the value is 0. Okay. So, one can easily capture the Jacobian in terms of this. Okay. So, this can be an exercise. Okay. This proof can be an exercise. I will include. So, now once we have the corresponding Lagrangian and Eulerian derivatives, what is the relation? Okay. So, as you can see, any fluid property f, it is expressed in terms of the position vector and time. You can see this position vector is with the reference variable x bar expressed in terms of the Lagrangian. So, now therefore, the Lagrangian derivative or the material derivative of this fluid property is nothing but the local rate together with following the trajectory. So, we would like to get the corresponding derivatives. So, you have an f which is x bar of this. So, df by dt is the local rate plus the following the particle. So, this is nothing but following the particle. Okay. So, this is the local rate. So, now this is nothing but velocity. So, which we will see. So, you can so in Cartesian frame. So, the summation I have expanded here. So, dou f by dou xi, dou x by dou t is expanded, and you can see this is a u bar. So, the entire thing can be expressed as this. So, that means we have the corresponding sometimes called substantial derivative is given by okay. So, this is the so very useful, because this will indicate how a particular fluid property is varying following the particle. So, not only local time, also the spatial trajectories. Okay. So, that is the advantage. So, once you have the convective derivative, we have discussed Jacobian and then we have convective derivative. So, you have apply convective derivative on the Jacobian, we get this, and this one can do using simple algebra. So, I would like to include this in the exercise. I am sure you will be able to do it. Okay. Right. So, we have now discussed how fluid motion can be described using Eulerian Lagrangian approach, and then how any fluid property, let it be velocity, density or temperature, how it gets convected. Okay. So, these variations we have discussed. So, now we would like to derive mass conservation, but before that we would require some tools. Okay. So, let us see the first tool, namely Reynolds transportation theorem. So, basically this indicates the variations of any fluid property or a fluid element and how it is changing with time. Okay. So, this is a Reynolds transport theorem. You can see we have considered a fluid element at time t equal to 0, bounded by a volume V, and the corresponding boundary is this, and this is the reference position vector, and it is along a trajectory, it has moved, and then this is the corresponding volume element at time t. So, we have indicated the normal as well here. So, now we would like to understand if there is any fluid property f which is continuously differentiable, how it gets convected and what is the rate of change of that particular fluid property over this volume element. Okay. So, you can see once you have f, the total amount is the integral of f over the volume element. Okay. This one. So, you can see this is the Eulerian description. So, now you come back to Lagrangian description. So, this position vector is expressed with reference to x bar, and the corresponding Jacobian and the corresponding volume element in the Lagrangian is given. So, now we would like to discuss the rate of change of this total amount. Accordingly, we compute the derivative. So, this is nothing but we are in Lagrangian frame. So, this is the corresponding Lagrangian derivative. Okay. So, you see this is nothing but the Lagrangian derivative, convective derivative. Okay. So, you expand, this is a simple calculus. So, once you do this, we use Euler's identity here. Okay. So, one step is missing. So, I would like to do this step here. So, consider this, okay, and then we use Euler's identity. So, once you use Euler's identity, we get see you have two terms df by dt j plus f dj by dt. So, we are using Euler's identity. So, f j. So, this is nothing but df by dt plus. So, we have taken the Jacobian out, further use the convective derivative. So, this will be u dot grad f plus f divergence u j, and these two are combined. So, therefore, we get okay. So, this is what we have written here. Okay. So, that is what we have got. Okay. So, the total rate of the total amount is equals to this. So, that means, if you take any fluid property f, let it be density or temperature or energy. So, over a fluid element, how it is changing is indicated by this. Okay. So, this is very useful tool to derive conservation of mass. Okay. So, as I indicated, so we are very much interested in the next conservation of mass, which is the first fundamental principle. Okay. So, according to this, a material volume V always consists, for example, if you do not have source and sink. So, then accordingly what will happen? Once you have a mass that stays, so no addition and no deletion is taking place, then total mass is conserved. So, always consists of same fluid particles. Okay. Therefore, mass must be preserved. So, accordingly the rate is this is the mass, and then rate is 0, okay, because the constants, the derivative of that will be 0. Now, apply Reynolds transport theorem with f equals to the density. Okay. So, you see this, we have the Reynolds transport theorem. If you take f equals to rho, right, density is, then this will be the mass, and if the total mass is conserved, d by dt of this is 0, and correspondingly f will be rho, we get the following. Okay. And you can see this holds for any arbitrary volume element. So, therefore, the integrand is 0, which is called equation of continuity. So, which is a fundamental equation. So, this is a general where you have density is varying. So, for example, let us say you have a 2D. So, then the above equation will be rho u rho v equals to 0. So, correspondingly, if you have 3 dimensions or polar coordinates, one can write similar form. Okay. Right. So, now there is a corollary to Reynolds transport theorem. So, let us say instead of f equals to rho, you take f equals to rho f. So, then d by dt over a volume element rho f dv is, again we apply the Reynolds transport theorem, and we expand, one term is coming here, one term from this coming here. Okay. Similarly, one term is here and one term is here, and this is nothing but the df by dt, and this is nothing but equation of continuity, which we have seen just now. So, therefore, this is 0 and this is the convective derivative. So, therefore, one useful identity we get is d by dt of rho times any fluid property is rho times the convective derivative. Okay. So, this is very useful identity, which will use it while deriving various other balance principles. Okay. Okay. So, now incompressibility condition for an incompressible fluid. So, that means we are talking about density variations are not there either with respect to space or time. So, correspondingly you have rho is constant, and then you get d rho by dt 0, and hence from equation of continuity we get divergence of u is 0. So, this is typically equation of continuity for incompressible fluids. Okay. So, now so far we have discussed the corresponding fluid description, and then Reynolds transportation theorem, which is which gives you how a fluid property gets convected along. So, once we do this, we should move on to the corresponding momentum balance, because that is the next natural principle. Okay. But before we go to this, we need to understand about forces. So, when you say forces on a fluid element, so these are expressed captured in terms of stresses. Okay. Typically either in solid mechanics or fluid mechanics, forces are captured in terms of stresses, okay, or vice versa, stress is captured in terms of a force. So, we would like to understand the concept of stress, so that we are in a position to move forward and get the conservation of momentum. Okay. So, what is stress vector? So, you apply a force on a element. Okay. So, that means let us say you have a surface, and then you apply a force. Okay. So, what will happen? So, force is applied on a particular surface. So, then what is the stress we would like to capture, right? So, the stress is defined as the force limiting of the force on a particular area. That means, the area is approaching to 0, and then the force acting on a particular surface element while the surface element is approaching 0. So, that is the stress. Okay. So, accordingly, you see we have taken a small element, okay, which has a normal, and then let us say this is the stress which we are going to define. How we are going to define is force on a particular surface element. These are indicated with plus, these are indicated with negative. So, action of these particles on these particles across small surface element. So, this is the force. Now, how a stress is defined? As I mentioned just now, limiting value of the force over area, okay, which means F bar by delta S is the stress vector, okay, as delta S approaching 0. Okay. So, now once we say stress vector, then that means this has components. So, those components are defined in terms of something called stress tensor. Okay. So, let us understand this stress tensor. Suppose you consider surface elements whose outward normals pointing along I j k. Okay. So, then the stress vector T I indicates that we are considering a surface element whose outward normal is pointing along I. Then it can be resolved along the 3 components. So, one is T 11, T 12, T 13. So, here you see we are talking about I. So, let us say I is 1. So, normal is along I. We are talking about stress on a surface having normal along I. So, then this is the I component, j component, k component. Similarly, you consider a surface element whose outward normal pointing along j. So, then here j is fixed, you can see, then this is the I component, j component, k component. Similarly, this is on a surface which is having normal along k. So, therefore, 3, we have 3. So, then this is x along I component, j component and k component. So, that means once you have a stress vector, we have 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2. So, this is called stress tensor. So, we have 9 components, 3 dimensions. So, this is called stress tensor. Okay. So, to be more precise, this is what I indicated. Tij is stress acting on a plane having normal along I and in the direction j. So, let us take an example. So, this is the plane, you can see normal is along k, okay, z axis along k. So, therefore, this is stress acting on a surface having normal along z and x component, normal along z, y component, normal along z, z component. Okay. So, these are the corresponding stress components. So, in Cartesian, suppose if somebody is using x y z, so this can be written as T x x, x y, x z, y x, y y, y z, z x, z y, z z. Okay. So, this is in Cartesian. Similarly, if you are using polar, correspondingly one can write down the corresponding components. Okay. So, now the most interesting is what will be the stress x y and y x. That means, we are considering, this means what? Stress acting on a surface whose normal is along x axis and the component is along y, and this one is stress acting on a surface whose normal is along y and component is x. So, we will see in later modules there will be an interesting relation between these two. So, which will be useful. Okay. So, understanding stress is very much important because this will give you the contact forces. Okay. So, as I indicated, once you have conservation of mass, what will be the next one is balancing momentum, right. So, momentum means we are balancing the forces. So, contact forces are very much play a role. So, in order to compute the contact forces, we have to capture the stress and then integrate the stresses. Okay. So, we will discuss in the next module how the stress will be integrated to get the momentum balance. Okay. Thank you.